Hello, we're going to talk about power and behavior models. Looking at this thing right here. And looking at it when it approaches, as the limit approaches infinity or negative infinity. The reason I picked this one is it's nicely laid out to show you and remind you of a few rules. And the first one is the sum and difference rules, which I'm going to put over here in like bright blue, is, if you don't know this, the limit as x goes to plus or minus infinity of a function, say f of x plus g of x, that is equal to the limit, this is a lot of writing here, as x goes to plus or minus infinity of f of x plus the limit as x goes to plus or minus infinity of g of x. So it's kind of like, I don't want to say it's like the distributive law, but it kind of is. I mean, it's like each one gets its limit. You can split things up that are added like that, where you have two functions or multiple functions added or subtracted together like that. If this was a minus sign here, do that in red. If that was a minus sign, this would just be a minus sign. So that's how that rule works. Now let's go back to our problem here. For this, we can apply the blue concept to this problem here. We can say that the limit as x approaches plus or minus infinity, we'll look at the graph and I'll draw a picture of this graph here in a minute, is equal to all of these things on the top divided by 3x to the fourth. So we could have 3x to the fourth over 3x to the fourth minus 2x to the third over 3x to the fourth plus 3x to the second over 3x to the fourth. I'm just writing each one here. 5x over 3x to the fourth plus 6 over 3x to the fourth. So this is true. We're using this sum and difference rule for infinite limits like that. Now, what we can do now is reduce these things. So let's do that. Okay, so I'm just going to write another big parenthesis here. 3x to the fourth over 3x to the fourth, well, that's 1, minus 2x to the third over 3x to the fourth, that is going to be 2 over 3x, plus, we're just reducing these fractions here. The 3's would cancel, and I would have x squared over x to the fourth, so that would be 1 over x squared, minus 5 over 3x to the third, because you got 1 on top, 4 on the bottom, and then plus 2 over x to the fourth. All right, so now we're going to plug in, well, you can't really plug in infinity, but you know, if you let these x's be 500 gazillion, these values here, because there's an x in the denominator, especially like these were x to the fourth, you know, take 500 gazillion to the fourth power, and you have a much bigger number even, and you're dividing here. So this translates into 1 minus 0 plus 0 minus 0. Let me back that out. Plus 0, which is 1. So now, what I'd like you to do is graph this. Graph this function, and I'll be right back, and I'll sketch a picture of it. Be right back. All right. So we got a little sketch of this graph, you know, and what I want to get to here is this in behavior model cares about the infinity out here and the negative infinity on the x-axis. You know, what does this thing look like as you evaluate this at infinity or negative infinity? And apparently this graph looks like y equals 1. Y equals 1, of course, is just a flat line at y equals 1. So this graph behaves exactly like the line y equals 1. And you can kind of see that infinity, when you plug it in for these values, that because this is to the fourth power, it is going to, as these numbers become bigger and bigger, it's going to like nullify these littler ones. Like the 6 isn't going to matter. If I plug a million in here, this 6 doesn't matter. The 5x doesn't matter because this is going to be so much bigger than everything else. So this behaves like 3x to the fourth over 3x to the fourth, which is, 1, 3x to the fourth over 3x to the fourth. So evaluating these end behavior models is very simple. You just take the biggest one on top and the biggest one on the bottom and divide them and cancel stuff. And this would, of course, become 1. So it behaves like y equals 1. All right, you guys have a good one.